Hello, here we are. We're in section 4.1, angles and radian measure. I divided this section into two videos, two parts. And so you'll see this on the objectives that are coming up. And if I were to just put it in one video, it would have been quite lengthy. So I decided to split this one up into two parts. So part one will consist of recognizing and using the vocabulary of angles. We're going to use degree measures, which is probably what you're more familiar with. We're going to use radian measures. Some of you guys may have heard of that one before. Some of you may not. We're going to learn how to convert from degrees to radians. We're going to also convert radians to degrees as well, by the way. And on those, the radians and degrees conversion, okay? It's not that hard. It's basically speaking two different languages. So when you're looking at degrees, which is probably more familiar with, when you convert that to radians, it may not make a whole lot of sense, at least initially. As we progress through this course, radians will become second nature to you guys. So anyway, we're going to also draw angles in standard position. Part two, which is our second video that you're going to be seeing, we're going to find coterminal angles and see what they are. We're going to find the length of a circular arc, and we're going to use linear and angular speed to describe motion on a circular path. So basically, the first part will consist of 5 objectives, and the second part only 3 objectives. So, alrighty. So let's begin. Okay, so what is an angle? So an angle is formed by 2 rays that have a common endpoint. One ray is called the initial side and the other ray is called the terminal side. So here they're calling the blue side BA, which is the initial side, and the terminal side they're calling that the red side, and they join at their endpoints. Still, now this definition of an angle is probably what you're most familiar with, since most of you guys had high school geometry, and so this is probably, again, this is what you're more familiar with. So now what we're going to do is we're going to kind of morph that into the trig approach. So an angle in standard position in trigonometry, if its vertex is at the origin, so you're placing the vertex on a rectangular coordinate system at its vertex and at its origin, and find the initial side lies on the positive x side. So the blue side is the positive x-axis. And the terminal side is where the angle terminates. So that's called the terminal side. So that is the idea. So that's what they are. Now, one of the big differences that you're going to see between angles in geometry and angles in trigonometry, for the most part, angles in geometry consist of any angle between 0 to 180 degrees, right? So it's half of a revolution. Well, in trig, they can surpass 180 by quite a bit. They can also be negative depending on the direction that you're going. So when we see an initial side of a terminal side in place, there are 2 kinds of rotations that could be generated by the angle. Positive angles are generated by the counterclockwise rotation. Thus alpha, okay, in this position, alpha is positive because you're going clockwise. Counterclockwise, and negative angles are generated by going in a clockwise rotation. So in this case, they're using theta, and theta is a negative angle. So understand the magnitude is the same, the measure is the same in a lot of times, but the direction that it goes, okay, depends on whether it's positive or negative. So in an angle that's called a quadrantal angle, is if its terminal side lies on x or y axis. So for example here, angle beta is an example of a quadrantal angle. So it's kind of, it sounds kind of weird because really when you have a coordinate system, if you remember, there are 4 quadrants. There's the first quadrant, there's a second quadrant, there's a third quadrant, and a fourth quadrant. But if the terminal side lies on an axis, it's called a quadrantal angle. So you would think it would be called an axis angle, but they don't call it that. They call it a quadrantal angle. So an angle that lies on an axis is called a quadrantal angle. Okay? So Measuring angles using degrees. Now, angles are measured by determining the amount of rotation from the initial side to the terminal side. So a complete rotation or revolution, we call it a revolution sometimes, is 360 degrees. So if you take 1/360th of a revolution, it's 1 degree. So the symbol is for the degrees, as most of you guys probably know, is that little open circle that's kind of put in the upper right-hand spot, or a corner of the actual number. So 360 degrees. So now these are just some common things that you should already know from geometry. An acute angle is an angle that measures less than 90 degrees. So it's between 0 and 90. A right angle measures exactly 90 degrees. An obtuse angle measures more than 90 but less than 180. And a straight angle is an angle that measures exactly 180 degrees. Okay? So that's just kind of a little summary of angles measured in degrees, which again, most of you guys probably already know this. So let's talk about radians for a little bit. An angle whose vertex is at the center of the circle is called a central angle. The radian measure of any central angle of a circle is the length of the intercepted arc divided by the circle's radius. So that's how you would measure the radian measure. So the length of the intercepted arc by the radius, divided by the radius. So what is a radian? Well, 1 radian is the measure of the central angle of a circle that intercepts an arc that is equal to the length of the radius of the circle. So let's look at the picture. So if you look at the angle there between those, if you notice the circle has radius r. The arc, which is where the two rays intersect the circle, the length around the circle from one point to the other point is also r, when those units are all the same. So if the radius is 5 inches and that arc is 5 inches, then the arc that's formed by there, meaning the angle that's formed by there, is 1 radian. So now, 1 radian is approximately 57 degrees, by the way. So let's say consider the arc length S on a circle of radius r. So they're showing you a picture. The measure of the central angle theta that intercepts the arc is the arc length S divided by r, and that's in radians. So the S, the arc divided by the r, is its angle definition. And remember, when S and R are the same, that equals 1 radian. So in order for that to be 1 radian, you'd have to pull that terminal side back over until it equals whatever the radius is in this picture. So obviously in this picture, theta is actually a lot more than 1 radian. So because if you divide S, which if you look at the picture is considerably longer than the R, when you divide the S by the R, it's going to be more than 1. So example 1, let's compute the radian measure. So if you have a central angle theta is with a circle of radius 12 feet, intercepts an arc of length 42 feet, what is the radian measure of theta? So theta is S divided by R, which is 42 divided by 12, which is 3.5 radians. So that is the measure of the angle in radians. Now, a lot of you guys probably can't really picture what that angle is. That is something that you're more familiar with. We will approach that coming up soon to figure out what is that actually in degrees. Because if I gave you 3.5 radians in degrees, just let me tell you, it's more than 180 degrees. So we know I know it's more than 180, but I'm going to show you in a bit what that angle, these kind of angles would, how you would figure those angles out in degrees. And here it is. So we know if we want to convert between degrees and radians, so we use the basic relationship that pi radians is 180 degrees. Now you're like, how do you know that? Well, if you have 1 radian, okay, you remember it's around 57 degrees. 2 radians is about 114. 3 radians, it's 114. 3 radians is about 171-ish degrees. So if you have 3.14, which is pi, that lands right on the 180 degree mark. So there's a relationship between those. So, okay. Now, Let's see. Well, and by the way, you also know it's pi radians for another reason as well, right? Because you know the circumference of a circle is 2 pi r. So if you have a radius of 1, it's the circumference is 2 pi. So it's 2 pi all the way around the circle. So halfway around the circle would only be pi. So the arc would be pi. But remember, the theta is measured by the arc length, which in this case is pi, divided by the radius, which is 1. So that's another reason we know it's pi radians. So pi radians is exactly 180 degrees. So if we're going to convert degrees to radians, we multiply the degrees by pi over 180. And if we want to convert radians to degrees, we multiply 180 over pi, just the reciprocal of that. So let's look at an example. So if we're going to convert an angle from degrees to radians, so we take the 60 degrees, and then pi times 180, which is going to be 60 pi over 180, and then it reduces down to pi over 3 radians. So now understand, okay, 60 degrees is basically 1/3 of a half of a revolution. I'll say that again. 60 degrees is 1/3 of a half of a revolution. Half of a revolution is 180 degrees, right? So 1/3 of that is 60 degrees. So and now pi is half of a revolution as well, right? Because remember, 2 pi is 1 complete revolution. So pi is that. So 1/3 of a pi, which is pi over 3, is also 1/3 of a half of a revolution. So that stands to reason that pi over 3 radians and 60 degrees are the same thing. Now, if you have 270 degrees, you multiply that by pi over 180, reduce, and it's 3 pi over 2. Now remember, 3 halves is 3 pi. 3 halves is basically what this is. It's 3 halves of a pi. So 3 halves is really 1.5, right? So 1 pi is, we know, half, and another half of a revolution is going to be at the 270 degree mark. So basically it's 3/4 of a revolution. So, and then negative 300 degrees. So notice the angle's direction. It's negative. So this angle is actually going clockwise. It ends up basically back up in the first quadrant. So we take negative 300 degrees, but it's still the same. You multiply by pi over 180, and then you reduce the math and down to negative 5 pi over 3. So the negative is the direction. Pi over 3 is the magnitude. The negative represents the direction you're going. So when you have a positive angle, you know you're going counterclockwise, and when you have a negative angle, you're going clockwise. So the negative is just going from the positive x-axis, going like a clock would go. So, okay. So, example 3. Now we're going to convert from radians to degrees. So pi over 4 radians. So we're going to multiply that by 180 over pi, and the pi's cancel, giving me 45 degrees. Okay? So, as a matter of fact, it says convert each angle in degrees to radians. It should be the other way around. It should be radians to degrees. I think the author made a mistake here again. So pi over 4 radians, yeah, that's in radians, and we want to convert to degrees. So I'm hoping you're understanding what's going on, okay? Pi over 4 radians and 45 degrees is representing the same angle. It's just basically a different language. Okay, it's just like when you're learning a foreign language. You know your primary language form of it, and then when you learn it, you translate it into what you know. So, for example, if I was trying to speak French to you, and I said the word oui, okay, now oui is actually yes in English, the conversion, but in French it's oui. So when I was learning that word, and I took some French classes, when I took that class, when I said oui, when I first saw it, I had, okay, what was that word again? Oh, it was yes in my language. So now if somebody is fluent in French, if somebody lives in France and they are fluent in that language, when somebody says oui, they don't have to convert it to English because they may not even know what English is. So they learn it, they know it from their primary language. But when you're learning that new language, you have to basically convert it to the language that you know. But what I'm saying to you is, as we progress through this course, when somebody tells you, oh, the angle is pi over 4 radians, you're going to know what that measure, that angle is before too long, okay, without having to convert it to 45 degrees. But for right now, you're going to have to figure out what pi over 4 is in the language that you know, which is 45 degrees. So they are equivalent. And when you have negative 4 pi over 3, again, you multiply by 180 over pi. The pi's cancel, and it knocks it down to negative 240 degrees. 6 radians. Now notice, there is no pi to cancel. So this case, there's nothing to cancel, so you got to multiply 6 times 180, which is going to be like 1,080. I think that's about right. And it'll be 1,080 divided by pi, which is 343.8 degrees approximately, if you're going to use a calculator. So if you notice, sometimes like A and B, there's a pi already in there. And so when you do the conversion, they cancel out really nicely. But in part C, 6 radians, so that one there doesn't have a pi in it. So you might, well, what is 6 radians? Well, 6 radians is almost a complete revolution. How do I know that? Because 343.8 degrees is almost 360 degrees, right? So it's not quite a revolution, but it is pretty close. And if you remember, pi was half of a revolution, so that would make 2 pi a complete revolution. What is 2 pi? 2 pi is about 6.28. And 6 radians is just a shy below 6.28. So 2 pi is 360 degrees, and 6 radians is 343.8 degrees. So there's that comparison. It's pretty straightforward there. You just got to know basically this 180 over pi formula here is basically our translation dictionary. So when you're learning that new language, you have a little dictionary of learning, okay, what is said, how does that convert to my language? And that's what's going on here. Okay? All right. So now we're going to learn how to draw angles in standard position. Okay? So the figure below illustrates that when the terminal side makes one full rotation, it forms an angle whose rating is 2 pi. So I've discussed that. That's the first picture. So that's 2 pi. Because half of a revolution is 1 pi. The full revolution is 2 pi. So what happens if you just go 3/4 of a revolution? Well, 3/4 of 2 pi, remember, was 3 pi over 2. We did that one a while ago, actually. So 3 pi over 2 radians is 3/4 of a revolution. So what about a half of a revolution? Well, we know that one as well. Remember, half of a revolution is going to be 180 degrees or pi radians, because half of 2 pi is 1 pi. So it's pi radians. So what if it's 1/4 of a revolution? Well, it's 1/4 of 2 pi. So that's pi over 2. And we can extend this a little bit more, so, and we will. I mean, what if it's what if it's half in the first quadrant? Well, then it's half of pi over 2. So that's pi over 4. And if you remember, pi over 4 was 45 degrees from a previous example. So here's negative pi over 4. So draw and label the angle in standard position. Theta is negative pi over 4. So there's the initial side, the blue. The red one is the terminal side, and it's negative pi over 4. Now notice the angle is going clockwise. Why is it going clockwise? Yeah, because it's got a negative in front of it. The angle is negative. It is obtained by rotating the terminal side clockwise. Now negative pi over 4 is equal to 1/8 of 2 pi. Now what's 1/8 of 2, right? What's 1/8 times 2 is going to be 1/4. So that's going to be 1/8 of a revolution. So we rotate the terminal side 1/8 of a revolution, and that's exactly where the red should go. So, and that is the angle. Now you're like, well, that looks awfully close to negative 45 degrees. You know what? It is. If you take negative pi over 4 and multiply it by 180 over pi, you get negative 45 degrees, because that's exactly what it is, just in our language. But in radian language, it's negative pi over 4. Okay? So draw and label the standard position of 3 pi over 4. So there is a picture of it, what it should look like. So the angle is positive, so we go counterclockwise. So 3 pi over 4 is actually 3/8 of 2 pi. Do you know why? Because 3/8 times 2 is 6/8. 6/8 reduced to 3/4. You're like, why are they doing it that way? It's because, well, they want to know what, because we know 2 pi is a complete revolution. So they want you to go 3/8 of a complete revolution. So if you do that, every quadrant is 1/4 of a revolution, right? So if you split the quadrants in half, each split is 1/8 of a revolution. So basically you're going to go 3/8. So 1/8 and 2/8 will cover the first quadrant. And then 1 more eighth will land it right there in that second quadrant where it's located. So that's exactly where the angle is going to be located. So we rotate the terminal side counterclockwise 3/8 of a revolution. And you're like, what is that angle in degrees? You can do this a couple of ways. I mean, you can think about logically. You remember, now you can say, well, I'm not very logical, so what I'm going to do is I'm going to use the formula. So yeah, you can multiply 3 pi over 4 by 180 over pi and reduce it. And then you would reduce it down to 135 degrees. That's what it would equal to in degrees. 3 pi over 4 is the same thing in our language of 135 degrees. But is there another way? Sure. You know, since you see the picture there, you know you know where the 90-degree mark is, and you know the red one splits the quadrant, so that's going to be another 45 degrees. Well, what's 90 degrees plus 45? Yep, 135 degrees. So there's a lot of ways to kind of visualize this, not just one way. All right, so example 6, we're going to draw angles in standard position. So draw and label the angle in standard position of negative 7 pi over 4. So we're doing the same thing. The angle is negative. It is obtained by rotating the terminal side clockwise because it's negative. Now notice where it should be located. It's going to end up, looks like splitting the first quadrant, but it's going clockwise. Well, if you remember, negative 7 pi over 4 is actually 7/8 of 2 pi. You're like, why is that? Well, because 7/8 times 2 is 14/8, and 14/8 reduces to 7/4. So it's going to be 7/8 of a revolution. Now remember, each quadrant, when you split it up, is an eighth of a revolution. So just count them over. So 1/8 and 2/8 will cover the full fourth quadrant. And then 3/8 and 4/8 will cover the third quadrant. So you're halfway there. 5/8 and 6/8 will cover the second quadrant. So you've surpassed the first, second, now the third. So if you go from the initial side all the way to the positive y-axis, you have gone 6/8. And then you need to go 1 more eighth. And that lands it right on where that red terminal side is. So that is negative 7/4. So, and again, you can actually do this in degrees. Change it to multiply by 180 over pi. And if you did, you would notice it's a negative 315 degrees. So negative 315 degrees is 45 degrees short of a revolution, which is exactly where it's located. So as you can see, I'm basically just rotating my languages. Okay, radians, degrees, I'm using them kind of interchangeably because there is a relationship between the two. So if I had started out this problem and said, draw me an angle that's negative 315 degrees and get it as close as you can, most of you guys could have done that. But if I said, okay, draw me an angle that's negative 7 pi over 4, that's when it gets complicated if you're trying to keep it in radians. So what I'm trying to do in these examples that you've seen here is try to draw a graph without doing that conversion. Okay, trying not to show you that anything about that negative 315 degrees. Where is negative 7 pi over 4 just by observation? So that's the challenge. So the challenge is not to convert it into degrees, but to use the given angle and to figure out where that terminal side is without doing that mental conversion in your head. Okay? All right. So we rotate the terminal side clockwise 7/8 of a revolution. Okay. I think we're going to do one more here, I think. Draw and label the angle in standard position of 13 pi over 4. Okay, notice where it's located. Okay. The angle is positive. It is obtained by rotating the terminal side counterclockwise. So remember, 13 pi over 4 is the same thing as 13/8 times 2 pi. Why again? 13/8 times 2 reduces to 13 over 4. It'd be 26 over 8, but that reduces to 13 over 4. So what you got to do is count 13/8 of a revolution. Now remember, each quadrant is 2/8, right? Because when you split it, it's 1/8 apiece. So 13/8, and just start with the positive x-axis. So 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, and 8/8. Okay, so that's a complete revolution, right? So if you have 8/8 of a revolution, then you've gone all the way around the circle. But you got to keep going. And then you go 9/8 and 10/8. That stops you back up on the positive y-axis. 11/8 and 12/8 will stop you on the negative x-axis. And we got to go one more, 13/8. And that lands you right there in the third quadrant, right there in the middle. So yeah, this angle is actually more than one revolution. So 13 pi over 4 is basically when an angle spins around, goes all the way around, and keeps going back, in this case, to the negative in the third quadrant, right there in the middle. So as you can see, it's different from geometry because this angle wouldn't even make really much sense in a geometry class because really our angle is measured between 0 to 180 degrees. This angle is actually more than 360 degrees, or 2 pi if you're talking in that angle. So this is actually more than one revolution. So angles can be negative, positive, very large, very small. And one of the things that really is not talked about very often is why do we talk about radians in the first place? Well, there is other reasons behind this, but suffice it to say for right now, I'll give this answer and it will satisfy us for right now. The reason we have this is because when the angle is huge, for example, what if you go around the angle, the initial side 3 times? What if your terminal side goes around 3 revolutions? Well, if you go 1 revolution, it's 360 degrees, right? Well, if you go another revolution, how much is that? Oh, it's 720 degrees. Well, that's not too bad. But what if you go around another revolution? Now you got to start thinking, okay, what's 720 plus another 360? And what is that without a calculator? So at this level, this reasoning is enough for us. There is other reasons besides this. But for right now, I'm going to leave it at that. Now, you know, well, what's that same angle in radians, though? Well, what's 1 revolution in radians? Oh, it's 2 pi. Well, then what's another revolution? Oh, that's 4 pi. Well, then what's another revolution? That's 6 pi. So 3 revolutions in radians is 6 pi. Whereas 3 revolutions in degrees is like 1,080 degrees or something like that. So when you go multiple revolutions in degrees, the angles become quite large, 4 or 5 digits sometimes. But if you're in radians, you know, if you go around 4 times, that's still only 8 pi radians. So it's a way to restrict the size of that angle. And again, that is a trivial answer to that question because there's much more to it than just that. But I'm going to leave it at that for right now as far as why we even discuss radians. That's a simplistic answer to that question. It's not the whole answer, but it's a simplistic answer to it. All right. So we rotated 13/8 of a revolution. Okay, so that concluded our first part of 4.1. Okay, so therefore we're going to be talking about the next ones coming up. So again, when you're looking at these videos, you need to make sure you pause it, write down the things that's important on it. Don't just listen to me and watch me do them. Okay. Sometimes you take notes in the class, right? Well, this is where you take your notes at. So if you didn't take notes on this, go back and watch this video again. Write down the important concepts, specifically the examples. And when you're writing them down, that's when you learn the material. Sometimes just listening to me is not good enough. It's you gotta be hands-on with this. So okay, so next video is coming up. So see you next time.